This is video number 1 for Computer Science 3344, Computational Theory. Welcome back from spring break to a brand new normal. It seems like months ago at this point that we actually even had a class. So I don't think it's a waste of time for us to start off with a quick review, at least of the recent stuff. We looked at abstract machines, non-deterministic finite automata, and all the things you could do with that. And we had just started talking about grammars. Well, I'll take that back. Regular grammars, we looked at those in some detail and stuff that you could do with that. But here are the big pieces. Grammar, represented by capital G, is a four-tuple. V, it looks like verse. V, and then capital sigma, which looks like an E, and R, and S. Verse. And I'll even elaborate on that and put what those pieces are. V stands for variables, which, if you recall at all, I don't like calling those variables. I'm not used to that. I'm used to calling them non-terminals. So that's what I'll go with. Non-terminals, which are individual symbols that have to be replaced eventually, or we do not have an official string of the language that's generated by this grammar. Capital sigma is the alphabet, but in grammar terms, for some reason, those are called terminal symbols. Let's see if we can reverse engineer why they're called terminal symbols. Well, non-terminals means you can't stop there, you got to keep going. Terminal means, yeah, you stop there. That is an official symbol of the language. So that's probably why they call them terminals. R is another one. R for rules. I'm used to calling those productions, so that's what I'll call them, productions. That says productions, and that's not an X, that's a T. There. Non-terminals, terminals, productions, and then this special, S is an element of V. S is the special symbol called the start symbol. Every string that's in the language can be generated by starting with symbol S, whatever that may be. It's typically S. But we start with S and then we use a derivation. In other words, we apply the production rules over and over and over again till we end up with a string of nothing but terminals, and that string of nothing but terminals is one of the strings that's in the language. That was supposed to be review. Here's more review. The Chomsky hierarchy of grammars, Chomsky. I don't remember if I mentioned him by name last time or before spring break or not. Hierarchy, Hierarchy. Noam Chomsky is a very famous and still living linguist and also a computer science theorist. So he actually has a lot of influence over this field. He's the one that decided how different grammars could be classified based on, actually it's based entirely on what their production rules look like. Here's a quick review of those. Type 0. That's actually the one we started with. Those are unrestricted. Anything goes. In fact, they're so wild and crazy, they're hardly useful for anything except theoretical purposes. They look like this. The production rules look like alpha goes to beta, where, like I said, anything goes, alpha and beta, as long as, I'll drastically abbreviate this, where alpha includes a non-terminal. Alpha has to have something out of V. Otherwise, if this is nothing but terminal symbols over here on the left, then we're done. We can't replace terminal symbols with other terminal symbols or anything else. So alpha has to have at least one non-terminal, but aside from that, there are not really any restrictions on the format of those productions at all. So that's the anything goes version of a grammar. Type 1, it's a little more restrictive. Each one of these is a sort of a refinement almost, or a restriction of the previous type. These are called context sensitive. All the pieces of the G equals VERS, all of those are the same, except the production rules have to be in this format. Alpha, capital A, beta can be replaced by, or I'll often read that as goes to, alpha, gamma, beta, which I won't write out a long definition over there, but let me describe this. What this is trying to tell us, indirectly perhaps, and rather abstractly, is that A, which is, unlike alpha and beta, A is a single variable or non-terminal symbol. A can be replaced by gamma in the context of alpha and beta, where alpha and beta are just anything that's any mixture, or even the empty string, any mixture of terminal and non-terminal symbols. So alpha and beta, those are still anything goes. Anything goes on the left, anything goes on the right. But A can only be replaced by gamma in this context. That's why it's called context sensitive. We might have several different productions that have capital A on the left, but they would have probably different contexts to show the different cases where A could be replaced with different things depending on what's surrounding it. And that's actually a much longer description that I would have tried to write down anyway. I hope that still makes sense. I hope it made sense the first time. It still makes sense now. Type 2. Type 2 grammars are context free. Poof, context went away. Context free productions look like this. Capital A can go to alpha, where alpha is any string of terminals and non-terminals. And you might say, well, that's very restrictive. I can only replace A if there's nothing around it. That's not true at all. This is really, by saying we can replace it context-free, is that we don't have to look at what's before A or after A to decide that we can replace capital A with this string alpha of terminals and non-terminals. In other words, it's context-free. We don't have to, now I'm actually repeating myself verbatim, we don't have to pay any attention to what's before or after A to be able to replace it with alpha. Maybe twice will be enough, and I won't have to repeat it 3 times. Type 3. Type 3 was our gold star grammar, if you recall, the regular grammar. That's the one we've done all that stuff with. Change it to a machine, change it from a machine back to a grammar, and derive all sorts of things. Why? Because the regular grammars are the ones that correspond to our non-deterministic or deterministic finite automata. Those go back and forth. Regular grammars generate regular languages, and then our finite automata, those recognize regular languages. So a regular language has productions like this. Very restrictive. A can go to little a, capital B. Those are not Greek letters because those are not strings of anything. Those are individual symbols only. Or we might have one that goes A goes to lowercase a all by itself without a non-terminal symbol after it. That's allowed. We might, in some special cases, well, actually one specific special case, if the empty string is on in the language, we allow S, the start symbol, to go to epsilon, the empty string, and I'll put maybe. Maybe we'll allow that. We'll have to allow it if the empty string is in the language, otherwise it's not there. And that's just saying that none of the other non-terminal symbols are allowed to go to epsilon, only the start symbol. So this one, again, no Greek letters here because a single non-terminal can be replaced by a terminal symbol, followed by a single non-terminal, or a non-terminal symbol can be replaced by a single terminal symbol. And you can go back and review your notes and remember that this is a one-to-one correspondence between all these different grammars that are regular grammars and all the different machines we can draw. All of our time spent on type 3 so far. Does all that make sense so far? Okie dokie. This is you know what? I'm going to do the same thing I do in class. Shame on me. I'm going to carve out a chunk over here. There. It's a whiteboard within a whiteboard. A miniature whiteboard. And I hope you can still see all that. Why? Because I'm going to go ahead and fill this up before I take the time to erase the whole board. Here's the definition, which we used whether or not I formally defined it or not, but I'm going to try to be more careful, more deliberate, since I don't get a chance to answer questions or anything. I'm going to try to fill in all the gaps up front that I can. The language defined, got to hold the board still. The language defined by grammar G You know what this is. I don't know that I made it official, but you know what it is anyway. The language defined by grammar G is written like this. It looks like a function. L of G, where G is in parentheses, equals this set of strings. Curly bracket, the set of all possible little W's. Whoops. Not ready for such that yet. W's that are an element of capital sigma star. I'll write and not try to describe as I write, and that way you'll make maybe less mistakes. Such that S with the double arrow goes to W. Now, it's not going to go directly in most cases, so we've got to put a star above that here. The star is just kind of as many as you want, or a wild card here. So let me see if I can, first of all, I hope you can read this. Let me read it back just in case. L of G, the language that's defined by G, is a set of all strings W out of capital sigma star, where S and the double arrow means we're using it to actually generate the string. We're using it in a derivation. It's not defining production rules if we use the double arrow. So it's the set of all strings W, capital sigma, 0 or more symbols out of our set of terminal symbols, where S can eventually get to W. That's what purpose that star is serving over here on the right-hand side. The star means 0 or more production rules in the grammar are applied to take S down to W. So S goes to something, that something goes to something else, that something goes to something else as many times as we need, thus the star. We can eventually get to string W, starting with the starting symbol and the rules of our language. For example, you know what? I am really going to pack this board full. I'm going to erase the whole thing. These are strange times. We ask that you bear with us. For example, let's put our comfortable old regular grammar shoe back on. Here's a regular grammar for you. A goes to lowercase a, capital B, or just, the vertical bar means I'm combining more than one production rule because I'm lazy and I don't want to write several lines. So A can go to lowercase ab or just lowercase a. Capital B, by convention, by the way, the capital letters are single non-terminal symbols. The lowercase letters are single terminal symbols. That's a convention when we're writing grammars. B can go to lowercase b, capital B, or just a plain old lowercase b. So that's an example of production rules of a grammar G, not fully written out, but typically we'll focus on the production rules anyway. A derivation using this, when I use it to derive things, I start with a start symbol, which in this case is A. By convention, that's the first production set I listed, so since there is no S in that grammar, by convention, A will be the start symbol. A, I'm going to replace that with, I can replace it with just an A. Ta-da! I'm done! I can't go any further. I can't replace a non-terminal with anything, so that's it. What are the philosophical implications of that? That's telling me that the string, lowercase a all by itself, is in the grammar, is in the language generated by this particular grammar. It's not a terribly enlightening example or not even terribly interesting. Let's do another one. Or maybe I start with capital A, slice and dice this board every which way but loose. Maybe this time, to make it a little more interesting, I'll use the first production here, A, capital B. My own personal convention, to make it easier to follow and easier for your instructor to follow what you've written, is to underline the non-terminals that are replaced at each step. In this case, there's only one choice, but I'm still going to stick to that convention. A, capital B, that is not a string in the language generated by G. It's called a sentential form. the form of a sentence in the language, if you will, but it's not officially a string of the language. It's of the right format. I didn't get there erroneously or anything. I'm just not done. So B, now I got to replace that with something. I could just replace it with B, but then it's not much more interesting than this one. So you know what? I'm going to keep going. I'm going to replace B instead with little b, capital B, which I'm allowed to do. I still got the A up front, but I rip out the capital B and replace that with lowercase b, capital B. That was so much fun. You know what? I'm going to do that again. That can be replaced by A, B, and then now I've got to replace capital B with something else. I got to keep going. How about another B? Capital B. You know what? We're having too much fun. So I'm going to call a halt to this and replace the capital B with a lowercase b, which I can do. A, B, B, B. The end. I have to stop there. Those are all terminals. Can't replace any of those. There, I've got a second string that's in the same language. Now, you're not going to have to think terribly deep thoughts to realize that in this case, the language defined by grammar G is... Pause and let you think of an answer. Starts with A, then 0 or more B's. How about this? A, B star. By George, I think we've got it. That's the language. We can write a regular expression for it. We could draw an NDFA that recognizes it. We could do anything we know how to do. Slice and dice that every which way but loose for regular languages. Because, look at this. This is a regular language. I think I said so at the very beginning. You could rewind the tape and find out. All the format fits for regular languages. So there we have it. Question on that? You know what? That's already a whole video's worth. I am really going to have to learn my pacing here. That's the end of video 1 already. I'll see you online.